So let's look a little bit closer at these layer 3 QoS markings. As I mentioned, we have this thing called DSCP. What this actually stands for is the differentiated services code points. Now, quite honestly, it's these values that are the main control mechanism for quality of service. Persistent via layer 3, and they happen to be more descriptive, thus more granular than IP precedence, because here's the thing, IP precedence had 3 bits with which we could do our markings, which gave us a decimal values from 0 to 7, whereas with respect to DSCP, we actually have 6 binary bits to play with. So what that actually really gives us is the values 0 all the way up to 63, which is in total 64 markings. So let's look at the terminology and the values associated with DSCP. So the first marking is referred to as EF. This is expedited forwarding, and pretty much this is the one that you really use when you want a packet to get top priority value. So expedited forwarding really is where you would mark your voice over IP packets. Now, numerically, what this actually maps to is the decimal value of 46. If you happen to have data that is real time for low latency, low jitter, we give it this marking of 46, and that's going to put it into the highest priority queue. So then we come to the next grouping. Now, this grouping actually is a range of values. Okay, this falls under the assured forwarding range. So this range is for things that are a little bit lower down in the priority. And what I will say is that this grouping can be a little bit confusing. So here's the thing, the way this is going to be categorized is we're going to have AF and then 2 other values. So let's say we have the value of AF11, this is a valid value, as well as something like say AF33. Now to be clear here, these are not the actual tags we put on the packets themselves. These are just general descriptions and categories that we use to describe the types of markings that we can use. So let's take for example this particular value here, AF33. Now the temptation might be for you to think that we're going to convert this into the decimal value of 33 and then thus derive the binary for that, okay? But this is not actually the case. As it transpires, AF33 actually correlates to the decimal value of 30, which means that the actual binary value is as follows, 011 110. Okay, stop the bus. Why is it like this? Why is 33 suddenly mapping to 30? What is going on here? Well, like I say, this particular value here is not meant to be a decimal value. In fact, it's actually broken into 2 separate values. Here is the first value, and this one here is the second. So the first value actually relates to the class, and the second value relates to the drop precedence. So basically, the higher the value here, the higher the class, the higher priority. And the higher the value here, the higher the chance that this particular packet is going to be dropped within its own class. Now, the first time hearing that is still really quite confusing. Let me just go through an example so that we can actually figure out what is going on here, okay? So let's say we have a packet we describe as AF33. And we also have another one described as AF31. So the first number, as we can see here, this is the class, and we can see here they both have the same number, thus are going to be put into the same priority queue. However, we obviously have different drop precedence, so in the event that this particular priority queue happens to suffer some bad congestion, the one with the lowest drop precedence is less likely to be dropped, meaning that this guy here is actually a little bit preferred to the top one right here, even though they're both going to go into the same queue. Let's do another one. Let's say we've got AF41 as well as AF13. What you're actually looking at here is the best possible AF value as well as the worst possible AF value. The reason being is that our AF class range can go from the value 4 all the way down to 1. So in terms of which packet is going to go into which queue, this one here is going to go into the best queue because it has the class value of 4. Now, out of all the packets it can go into Q4, this one has the lowest drop precedence of 1, whereas this one here, out of all the packets that go into the 1 queue, this one has the highest drop precedence of 3. So just to be clear here, with respect to AF, the class can range from 1 to 4, and the drop precedence can range from 1 to 3. So in this one here, the higher the better, and this one here, the lower the better. So say for example, if we happen to have AF43 and AF41, so which one is going to be better? Well, straight away we look at the first number, which tells us the class. They're both in the same class. However, if we happen to have congestion, let's look at the second number. AF41 has the lower drop precedence, therefore this is going to be less likely to be dropped. This one is going to win. Whereas if we happen to have AF11 versus AF13, like I say, they're both in the same class, so they have the same queue. However, if we happen to have congestion within that particular queue, which one is more likely to be dropped? Well, this one here has the highest drop value, therefore this one is more likely to be dropped. Therefore, this one here is actually going to get the better priority overall. I know, it's not the best system. I didn't design it like this. I'm just trying my best to explain this weird and wonderful behavior, okay? Now, circling back, how on earth do we get from AF33, remember this, how on earth is this somehow equating to the decimal value of 30? Well, there actually is. Well, there actually is a formula that we can use to derive the value. Now the formula is as follows. What you do is you take the class number, which is the first number, and you times it by the value of 8. And then what you do is you take the drop precedence value and you times that by the value of 2. And what you do is you take these two values and add them together. So let's run the calculation. Class value times 8, that is 3 times 8. Again, I'm going to add it to whatever the drop precedence is, which in this case here is 3, and we're going to do 3 times 2. So what this translates to is this value here, 3 8s are 24, and we're going to add 24 to 3 times 2, which is add on 6. That gives us the value of 30, thus AF33 is the decimal value of 30, thus why it looks like this. This is the value 1, 2, 4, 8, 16, and 32. So what do we have turned on? 16, add 8, add 4, add 2. If you add them up, this becomes 30. Now to be clear here, when we actually mark a packet to be AF33, there is nothing on the packet itself marked as AF or the values 33. It simply is that binary value, okay? So it's just this marking here as follows. This is just the binary we put in the type of service header inside the IP packet. And another one, which is obviously very important, is just having regular old traffic, which is marked DSCP0. This is casually referred to as best effort traffic, pretty much meaning that the devices will give their best effort to actually transit that data, and this is a much more relaxed approach, kind of like, you know, I'll do my best. This is your regular non-priority traffic, such as your data downloads, perhaps your web traffic, just general browsing of the internet, whereby a delay can happen. We can just wait a little bit for the page to load. So realistically, as a brief recap, for our voice traffic, you want to be utilizing EF, which is expedited forwarding, otherwise known as decimal value 46. We have our weird and wonderful AF ranges. This can be used to classify things such as video, which is not quite as important as, you know, your voice data. And then we can have our best effort traffic, which is going to be our DSCP value of 0, which is pretty much going to encompass all your traffic that does not require any prioritization.